Good day everyone. I'm James Brilliant Celedonio from BSAE 3-1, and today I'm gonna discuss my answer in item number 1 of quiz number 2 in aerodynamics 1. Let's read the question. Flying at 35,000 feet, an aircraft is flying at a speed of 460 miles per hour. If its airfoil has a chord measurement of 3 meters and a span of 10 meters with a trend of the pressure distributions given as y upper equals negative 0.746 minus 0.059x plus 0.00988x squared and y lower equals 1.413 minus 0.3442x plus 0.01918x squared, where x is in feet respectively. Calculate the value of lift coefficient and lift. So I have here my document of the answer that I've got from the question. So let's discuss further. So first, let's identify the dimension analysis. So we have the given chord measurement of 3 meters. We will convert all the given measurements to its empirical unit conversion. So 3 meters times the conversion factor of 3.281 feet is equal to 1 meter. So that would be 9.843 feet for our chord measurement. For our span of the chord, we have 10 meter times the same conversion factor, 3.281 feet over 1 meter, equals 32.81 feet for our chord span. Next, for the velocity, we have 460 miles per hour. We're gonna convert it to feet per second by multiplying the conversion factor. 1 mile is equal to 5,280 feet times 1 hour over 3,600 seconds. We're gonna have 674.666667 feet per second. So let's store that in function A. Next is our surface area. We're gonna just multiply the chord measurement by the chord span. So that's just 32.81 feet times 9.843 feet. We're gonna have the value of 322.94883 feet squared. So store that in function B. Now let's proceed to our solution or the supporting data. So this is the required, the coefficient of lift, and the lift itself. So to compute the coefficient of lift, we have CLO or the CL value obtained at low speed over square root of 1 minus m squared or the Mach number. For the lift, um we have the dynamic pressure times surface area times the coefficient lift that we will be obtained from this one. So to compute for the coefficient lift, we need to first identify the Mach number. So to compute naman for the Mach number, we need to first identify the ambient temperature. So we will be using the given altitude to compute for the ambient temperature using SSLC conditions or under SSLC conditions. So T is equal to T naught plus lambda times H. So 519 degree Rankine plus the lapse rate negative 0.003566 degree Rankine over feet times the altitude or height, which is that is supposed to be 35,000 feet. Let's double check it. Negative 0.00566 So it's 35,000 feet, and we will have the ambient temperature of 394.19 degree Rankine. So we're gonna input the temperature to compute for our Mach number. So m for the computation of Mach number, we have the formula m is equal to v over the speed of sound, or is equal to square root of rho RT. So v, which is stored in function a with unit feet per second, over square root of the density under SSLC condition 1716.225 pound-feet per slugs degree Rankine, times 1.4, which is the um, R for air, times our computed ambient temperature of 394.19 degree Rankine. So upon computing the Mach number, we're gonna end up having 0.6932427.275. So we're gonna store that in function C. So since our Mach number is under the computation using the Prandtl-Glauert rule, which states that if the Mach number is between 0.3 to 0.7 or less, we're gonna use the formula the for the coefficient of lift with this formula. So CLO over square root of 1 minus m squared. So this one, since we have a 0.6 Mach number under Prandtl-Glauert rule. So in order for us to compute for that, we also need the um, uh, CL value obtained at low speed, or the CLO. So we have this formula for the compression correction. So CLO is equal to 1 over C times the integral of this is the difference of pressure coefficient, lower and upper. So we have 1 over C, or the chord measurement 1 over 9.843 feet, times the integration of our given lower pressure coefficient minus the upper pressure coefficient. So 0 to 9.843. So we just need to simplify this. So 1.413 minus negative 0.746, we have positive 2.159. So negative 0.3442x minus negative 0.059x equals negative 0.2852x. Next is 0.01918x squared minus 0.00988x squared equals 0.0093x squared dx. So we can now integrate this function. So we have 2.159x minus 0.2852x squared over 2 plus 0.0093x cubed over 3 from 0 to 9.843. So we're gonna just distribute the difference. So 1.91 over 9.843 times so we're gonna have 2.159 times 9.8 0.43 minus, it's just 0 since we're gonna just multiply 0 to um this term of the function. So it's just minus 0 for all the term. So in feet. So if we compute this, we're gonna have our CLO equals 1.055730612, and we will have to store that to function D. So since we now have the uh, coefficient of lift value obtained at low speed, we can now compute for the coefficient of lift itself. So the D function, which is the CLO over the 1 minus Mach squared, Mach number squared, wherein our Mach number is stored in function C. So we're gonna end up having 1.464859835 for the coefficient of lift. So store that to function E. So now let's compute for the lift itself, since we already have the lift coefficient. But before that, we need to find first the um, dynamic pressure in order for us to compute for the lift. So dynamic pressure formula is half rho v squared. So we're gonna use the uh, density formula. Rho 1 over rho naught is equal to 1 plus lambda h over E naught raised to 4.26. So in order for us to get the um, density, we have uh, conditions under SSLC times the height given to us earlier. So 0.002377 slugs per feet cube. Our density with its imperial unit times 1 plus negative 0.003566 degree Rankine over feet times the altitude of the aircraft, 35,000 feet, over the temperature on the SSLC, 519 degree Rankine. So we're gonna have density equals 7.364141161 times 10 raised to negative 4 slugs per feet cube. So we're gonna store that to function F. So after that, let's compute for the dynamic pressure equals 1/2 times density, which is stored in function F, times the velocity squared, which is stored in function A. So 1/2 F slugs per feet cube times A squared, feet square per second squared, equals 167.5986886. So that's 167 slugs per feet second squared. So store that to function M. So we can just plug in it to our lift formula. So to compute for the lift, we have the dynamic pressure times the surface area times the coefficient of lift. So we have dynamic pressure stored in M function slugs per feet, surface area stored in V function feet squared, times the dimensionless E, or the coefficient of lift. So upon cancellation of units, we're gonna have just the unit of pound force. So lift is equal to 79,286.71101 pound force. So this is now the answer with 3 decimal values. Coefficient of lift equals 1.465, and the lift is equal to 79,286.711 pound force. So that's it for the question number 1.